In 1940, a brand new steel bridge tore itself apart in a wind of just 40 miles an hour. The force that destroyed it was not a storm. It was vibration, the wind pushing a blunt shape back and forth until it shook itself to pieces. That same force can be captured and turned into electricity using nothing more than an $18 length of galvanized pipe. No blades, no bearings, nothing that spins. The pipe simply vibrates in the wind, and that shaking becomes current. A Spanish company already sells turbines built on this principle, and researchers are actively refining it, yet it appears on no energy incentive list in the country. It's called vortex-induced vibration. By the end of this video, you'll know exactly what it is, why a solid pipe shakes, and how to build one yourself for the price of lunch. Let's dive in. A small residential wind turbine, the kind you mount on a pole or a rooftop, costs anywhere from a few hundred to a few $1,000s. And the uncomfortable truth is that most of them never earn it back. The problem is not the wind. The problem is the machine. Every spinning turbine, from the largest utility tower to the smallest garden model, shares the same handful of weak points. It has bearings, and bearings wear out. It has blades, and blades flex millions of times until the material fatigues and cracks. It has an alternator or a gearbox that needs servicing, and often brushes that erode with use. Each of those parts is a repair waiting to happen, sitting on top of a pole where reaching it is its own problem. Then there is the wind itself. Every turbine has a cut-in speed, a minimum wind it needs before the blades will turn at all. Below that, in light or gusty air, it sits motionless and produces nothing. It is noisy when it does spin, it kills birds. And it despises turbulence, the swirling, broken wind that pours around real rooftops, walls, and trees, which is exactly the wind most homes actually have. So the machine you bought to be simple and passive turns out to be neither. It is a moving assembly exposed to weather, working hardest in the worst conditions. A blade is a moving part, and every moving part is a maintenance schedule with a countdown. But there is a way to pull power from wind with nothing that spins at all. Stand a pole in the wind and it does not just stand there, it shivers. You have seen this 100 times without naming it. A flagpole hums in a stiff breeze, a tall road sign buzzes and trembles on the highway, a radio antenna whips back and forth. That motion looks like nothing, a nuisance, if anything, but it is not nothing. It is mechanical energy, and the wind is pouring it into that pole continuously, for free. Now, imagine capturing it. If you can turn that shaking into electricity, you have a generator with no blades to fatigue, no bearings to seize, and no gearbox to service. It does not spin. So there is nothing to lubricate, nothing to wear against anything else, and nothing to replace when it fails, because the failure never starts. The obvious question is how a solid, motionless pipe becomes an electrical current. The physics has a name: vortex-induced vibration. Here is what happens. As wind flows past a blunt cylinder, it cannot wrap cleanly around the far side. Instead, the flow peels away and rolls up into a swirling eddy, a vortex that detaches and spins off downwind. Then another forms on the opposite side and sheds the other way. First one side, then the other, in a steady, alternating rhythm. Engineers call this trailing pattern a von Karman vortex street. Each vortex, as it lets go, gives the pipe a small, sideways tug. Because they alternate, the pipe gets pushed one way, then the other, then back, a rhythmic shove, in time with the shedding. Now the important part. Every object has a natural frequency, a rate at which it wants to sway, the way a plucked guitar string wants to vibrate at one pitch. When the rhythm of the vortices shedding off the pipe happens to match the pipe's own natural sway, the two lock together. Engineers call it lock-in, or resonance. And when that happens, the motion stops being a faint tremble and grows into a real, visible oscillation. Small pushes, perfectly timed, add up. That gives you movement. To turn movement into electricity, you add one more piece. Fix a piezoelectric element at the base, a crystal that puts out a pulse of voltage every single time it is bent. Or wrap a magnet and a coil so the swaying drives a current by electromagnetic induction. Either way, every flex of the pipe becomes a pulse of power. Be clear about the scale though. For a pipe this size, the output is small, microwatts to milliwatts, a trickle that has to be collected and stored, not plugged straight into a lamp. And if you doubt how much force a little resonance can build, one bridge settled that question in 1940 in front of a film camera. On the morning of the 7th of November 1940, over Puget Sound in Washington state, a brand new suspension bridge began to move in a way its builders never imagined. The Tacoma Narrows Bridge had opened just 4 months earlier. On that morning, the wind was blowing at only about 40 miles an hour. Not a hurricane, not even a severe storm, a stiff, steady breeze. But the bridge's deck had been built from solid steel plate girders, a blunt, flat wall that the wind could not pass through cleanly. So the wind did to that deck exactly what it does to a pipe. It shed vortices, and it began to push. At first, the roadway rippled up and down in slow waves. Then the motion changed into something worse, a violent twisting, one edge of the deck rising as the other fell, corkscrewing back and forth by several feet. And here is the mechanism that matters. The wind was feeding energy into that motion faster than the structure could absorb it. Every oscillation made the next one bigger. Engineers call that negative damping, a system where the shaking amplifies itself instead of settling down. It could not survive it. The deck tore itself apart and dropped into the water below. Now, one honest correction, because the accurate story is better than the myth. For decades, textbooks blamed simple vortex shedding resonance. Later analysis complicated that. The frequency of the bridge's twisting did not actually match the vortex shedding rhythm, which means plain vortex shedding was not the whole cause. The real culprit was a related but more intricate instability called aeroelastic flutter. But the lesson underneath survives either way. Wind moving past the wrong shape can pour its energy into that shape until it moves with astonishing violence. The bridge did not need a hurricane, it needed the wrong shape and a steady breeze. That is the exact effect a bladeless harvester tames, shrinks, and puts to work. And the obvious question is whether anyone has actually done it. Someone has. A Spanish company called Vortex-Bladeless has spent years building exactly this. Their turbines look nothing like a windmill. Each one is a slender vertical mast, a cylinder made of resin reinforced with glass or carbon fiber, the same materials used in conventional turbine blades anchored at the base and left free to oscillate in the wind. No blades reach out from it, no rotor turns. It simply stands there and sways, and an alternator at the base converts that sway into current. Their smallest published prototype, the Vortex Nano, stands about 1 meter tall and produces roughly 3 watts modest, but enough to trickle charge a battery for small off-grid electronics. A larger model, which the company named the Vortex Tacoma after the bridge, pointedly stands about twice as tall and is rated up to around 100 watts, aimed at residential and agricultural use. The company reports that producing these masts can cost up to about 53% less than a comparable bladed turbine, with no gears and no lubricants anywhere in the design, and this is being taken seriously in the lab. In 2025, researchers at the University of Glasgow ran simulations across thousands of design variants and identified an optimized shaft geometry that could safely deliver up to 460 watts of peak power, well beyond the best prototypes built so far. So the technology is real, it is funded, it is commercial, and it is being actively refined. Which raises the question you should be asking by now. If a bladeless harvester works, why is it not on your roof or on a single incentive list? Because of a number the brochures move past quickly. It comes down to efficiency. A spinning blade sweeps out a wide circle, and it can pull 40 to 50% of the energy from all the wind passing through that circle. A vibrating cylinder does not sweep anything. It only interacts with the thin slice of air right around it. When independent researchers calculate its power coefficient, the fraction of wind energy, it actually captures the answer lands between just 2 and 6%. That is the whole story in one comparison. For the same wind, a bladeless harvester captures a small fraction of what a bladed turbine of similar size would. It has a second limit too. It only works well in a narrow band of wind speeds, near the speed that drives it into resonance. Too slow, and it barely stirs. Too fast, and the resonance breaks and the motion falls off. And you cannot simply crank up the amplitude to harvest more, because a bigger, harder swing is the Tacoma problem in miniature. Push it too far and you shake the structure to failure. That is precisely why commercial versions have stayed between 1 and 100 watts. The ceiling is not a lack of effort, it is physics. Then there is the paperwork, which finishes the job. There is no bladeless turbine lobby, there is no trade association, there is no underwriter's laboratories listing for a shaking pipe. And without a listing, no inspector approves it, no insurer covers it, and no appraiser gives it value. Nobody suppressed this technology, the incentive lists reward watts and certifications, and a resonating pipe delivers neither at scale. So let me be direct, because this channel exists to cut hype, not sell it. No turbine needed is true, but the pipe does not beat the turbine. It trades most of the wind's energy away in exchange for having nothing that can break. For the right job, that is a trade worth making. It does not outpower the turbine, it outlasts it. So, the real question is not whether $18 of pipe can run your house. It cannot. The question is what a silent, unbreakable trickle of power is actually good for. A wireless soil sensor needs microwatts. A small weather station needs a little more. A remote gate sensor or a trail camera needs a small stored charge topped up over time. None of these need watts. All of them can be fed by a pipe shaking in the wind. And here is the job it does that a turbine cannot. Picture a spot where running a wire is impractical and a solar panel would sit shaded under trees or glazed over with ice half the winter. A bladeless harvester does not care. It has no blades to ice up and no bearings to freeze. It sits silently, harvesting whenever the wind moves, and banks the charge for when the sensor needs it. That is the honest use case: silent, blade-free power for a low-draw device in a place a turbine or a panel would struggle. If you want the complete build, with the harvester wiring and the tuning steps laid out, we put together a guide covering everything in this video and more. The link is in the description below. Here is how you build it. The mast is your $18 length of galvanized steel pipe, roughly a 1/2 to 3/4 inch across and a few feet long. You want it light and stiff. Stand it upright and anchor the base firmly, but leave the length of it free to flex, so the top can sway. That freedom to bend is the whole point. Now, the conversion. Fix a piezoelectric transducer at the base, where the bending stress is highest. A cheap piezo buzzer element works, or a purpose-made harvesting disc. Every time the pipe sways, it flexes that element and it emits a pulse. Wire the piezo through a bridge rectifier to turn its alternating pulses into steady DC, then into a small energy harvesting circuit and a supercapacitor that collects and holds the trickle. Tuning is what separates a build that works from one that just sits there. The pipe's length and any weight you add at the top set its natural frequency. Adjust them so the pipe's sway lines up with the wind you usually get, and place it where the wind swirls, not where it runs smooth beside a wall, at a roof edge, in the broken air where a bladed turbine chokes. That turbulence is exactly what wakes this one up. One critical warning, and it is not about performance. Keep it small and keep it anchored. The same resonance that makes this work is the effect that destroyed a bridge. A large or poorly secured pipe swaying hard next to a window or a person is a genuine hazard, not a decoration. There are hard limits here, and you should hear them plainly. An $18 vibrating pipe produces microwatts to milliwatts, not watts. It will not run an appliance, charge a phone quickly, or make a dent in your power bill. It needs wind, and it needs the right band of wind in dead calm. It gives you nothing. Its efficiency is a small fraction of a real turbine's, and no clever home build changes that number, because the number is set by physics. This is a sensor and trickle device. It is not a power source. What it gives you instead is wind power with nothing to seize, nothing to lubricate, and nothing to replace running quietly in the swirling, broken wind that defeats spinning blades. This is not a suppressed miracle. It is an honest trade. The energy market has no box to file. Less power in exchange for almost nothing to break, in the exact turbulent corners a turbine cannot use. If discovering the quiet, unglamorous, honest corners of engineering matters to you, subscribing and sharing is the simplest way to make sure this kind of knowledge keeps being found. We will be tracking all of it as it develops. So here is the question. Would you stand an $18 pipe in the wind to shiver out sensor power for years with nothing that can break? Or would you still bolt up a small spinning turbine that makes more right up until the bearings go? I'd genuinely like to know. Drop it in the comments.